We can start with ammonia, NH3. That's always a good one to start with. Actually, why don't I start with potassium ion? Because I'm interested a little in how that's represented, because I've noticed there's two distinct ways of writing potassium ion. So if we look at potassium, potassium's in which group? On the periodic table?
Group 1.
Group 1. So how many valence electrons would you expect potassium to have?
1.
1. And so that's the 4s1 electron. That's in the outermost level. And so, okay, fine. It's in the outermost level. And that's potassium metal. So when we have potassium ion, it becomes +1. And so how many valence electrons would you expect potassium ion to have? So this is now gone. How would you represent potassium ion with valence electrons?
It's got 1 valence electron.
It's got what?
1 valence electron.
Now, potassium metal has 1 valence electron. Potassium metal without a charge has 1 valence electron, but then it loses it. It loses
0.
So 0. On the other hand, what is isoelectronic with potassium ion? How would we represent this in a noble gas configuration?
Would start with arsenic? Argon?
Argon, right. It looks like argon, because potassium metal has 19 electrons. Potassium ion has 18 electrons, just like argon has 18 electrons. But when we write argon, how many electrons, how many valence electrons do we give to argon?
6.
What group is argon in?
It's there's 8 valence electrons. It's
right. It's a noble gas. So we would go 1, 2, 3, 4, 5, 6, 7, 8. So the thing here is, I've seen it both ways. So I've seen, K plus with no valence electrons, and I've also seen it with 8. Either one is correct. The thing is, since it isn't actually making any covalent bonds, it doesn't really matter. It's the charge that matters. The number of valence electrons that it has isn't really that important, because it's the charge that's making the bond, not the electrons. So if you want to make it with 8, or if you want to make it with 0, either one is fine with me. To be honest, I'm probably not going to be asking a lot of questions about it on tests, because, as I mentioned, valence electrons aren't really involved in ionic bonding. It's the charges themselves that are involved in ionic bonding. This valence electron of the potassium metal is given away. It's not shared. It is gone. And so because it's gone, that creates a charge, and it's the charge that's doing the bonding. So if you want to make it with 0 or you want to make it with 8, either way is acceptable. However, whichever one you feel more comfortable doing. Okay. So is there another one? Oh, I mentioned, ammonia. Ammonia is always a good one to get started with. So let's look at ammonia. Good old NH3. So how are we going to draw out ammonia? Which goes in the middle? We've got two choices. We can either put nitrogen in the middle or we can put hydrogen in the middle. Which one's going to go in the middle? What do you think?
Nitrogen.
Nitrogen, right. And why would you put nitrogen in the middle? A nitrogen is more electronegative than hydrogen. Why would you put it in the middle?
The very well, there's three of them. There's three hydrogens, and they each only are allowed one bond.
Right. Hydrogen never goes in the middle because hydrogen can only make one bond. And so, yeah. So even though nitrogen is more electronegative than hydrogen, it goes in the middle because it can form 3 bonds and hydrogen can only form 1. So you put nitrogen in the middle, and I put 1, 2, 3 hydrogens around it. And then I put my 1, 2, 3 bonds. So let's count up the number of valence electrons we have here. So how many does nitrogen have? Soon you'll be able to do this right off the top of your head. Nitrogen, how many? Yes, Ferris, 5. Nitrogen has 5. And hydrogen, 3 times how many? Man, you type fast, man. 3 times 1. So we have a total of 8 valence electrons. So how many valence electrons are in bonds right now?
6.
6, right. We've got 1, 2, 3, 4, 5, 6. So there's 2 left over. So first we look at, if there's leftover electrons, first we go around the outside, and we see if any of the outer elements need additional electrons. And we see that each of them are hydrogen, and they each have a bond. So 2, so they're good. They don't need any more electrons. And so when we have leftover electrons, after we've gone around the outside, we put them in the middle. So we put them on nitrogen. So then you can see that each hydrogen has 2 electrons, as they should. And nitrogen now has how many?
Eight.
Nitrogen is 8, right. It's got 2, 4, 6 in the bonds, and it's got these 2 for a total of 8. So the hydrogens are all happy. The nitrogen's happy. There's no charge, so there we go. That is our final Lewis structure for ammonia. Now I want to do one that's not I don't think it's included here, but it's one that's important. It is ammonium ion. Now ammonium is one of the few positively charged polyatomic ions. So let's do this one. So how many, so we know we're going to put nitrogen in the middle. And this time it's got 4 hydrogens. So 1, 2, 3, 4. Then we put 1, 2, 3, 4 bonds. So how many electrons are going to be in the ammonium ion total? How many valence electrons?
Is it
Well,
still
you get 5 from nitrogen, right?
Yep.
And then you get, yeah, what Ariana said. And then you get 4 from hydrogen.
Yep.
And, but then you have to subtract 1 because of the plus.
Bingo. Yes, there's 9 valence electrons minus 1 because there's a plus charge, meaning there's 1 fewer electron than the neutral molecule. So instead of having 9, we take away 1 and we only have 8. So let's go around. How many electrons do we have in bonds?
8.
8. So there are no electrons left over. So you're done. This is finished, and we would put like a bracket around it and a plus. But where do you think the plus charge is in here? And how would we figure it out?
You mean like where on the molecule it is?
Yes. Yeah, exactly.
Or is it on the nitrogen?
Mm-hmm. Why would you say so? Yeah, we would put the plus sign there. How
Because like
come?
I don't know, it's like where your nitrogen is kind of like, I would say, the core of the bonding. So then
It's not
since
always
it's
going to be
where,
there though. But usually, yes, usually you will find if there are charges, if there are positive charges, they're generally in the middle. Negative charges tend to be on the periphery, but not always. That's not always the case. But how would we calculate that, do you think?
Is that where you would use the formal charge, the valence minus?
Exactly. Very good. So let's figure out what the formal charge would be on nitrogen. How many valence electrons does nitrogen have? Well, it's supposed to have 5, right? So we put down 5. And then we subtract the number of valence electrons it actually can say are mine in this particular structure. So remember, each bond is 2. And while they're sharing electrons, each atom gets to claim both of them for filling up its valence shell. So hydrogen has its 2, it's happy. Nitrogen has its 8, so it's happy. But when we're determining formal charge, we have to look at only the electrons each element can say are mine. And so that's half of each bond. So we basically just cut them in half and say, hydrogen, you have 1, nitrogen, you have 1. And so as we go around, we see that how many valence electrons does hydrogen get to claim as its own? Each hydrogen is the same. So how many valence electrons does each hydrogen get to claim its own when determining charge? You only get half the electrons in a bond that you say are mine. Yeah, Ferris says it. 1, right? Because each bond, we break it in half and we say you get this, one atom gets this one, the other atom gets the other one, and that will determine the actual charge. So hydrogen has 1, 1, 1, 1. Each of them has 1. And how many valence electrons should hydrogen have? What group is hydrogen in?
group 1,
How many valence electrons should it have?
1.
1. So it should have 1 valence electron, does have 1 valence electron, so its charge is 0. So hydrogen is not charged. Let's look at nitrogen. Nitrogen is supposed to have 5 valence electrons. How many does it actually have in this particular construct? So there's 8 total valence electrons in this model of ammonium ion. Now we've already said hydrogen's got 4 of them. Each of the 4 hydrogens has 1. So how many are left? Ariana, right. 4. There's 4 left. There's that one, that one, that one, and that one. Those are the 4. There's 4 bonds that hydrogen's making, and so it can claim 1 of those electrons for its own charge. And so it only has 4. Therefore, the difference is +1, and That's the charge. So nitrogen has a +1 charge in this particular, in ammonium ion. And that's where the +1 charge comes from. Because nitrogen is supposed to have 5 valence electrons. Nitrogen is supposed to make 3 bonds for 3 electrons and have its own lone pair for 2 more, for a total of 5. But in this instance, it has 4 bonds instead of 3, with 1 electron each and no lone pair for itself. So it's missing an electron that it usually has. And so it has 1 less than it usually does. And so it is +1 charge. Okay? You see the difference between when nitrogen has 4 bonds and nitrogen has 3? It changes the charge on the nitrogen. Okay. Who wants to pick out one to do next? Oh, is it there? I mean, I'll definitely do it because that's a really fun one to do. Yeah, Ryan. Okay, we can do that one. Ryan suggests carbon monoxide. Is that one of the? I can't remember if that's. Oh, it is. Cool. Yeah, carbon monoxide is very cool, and we had the question about it this morning. So, yeah, carbon monoxide is a very interesting molecule for a lot of reasons. So we'll do carbon monoxide, and then we'll do carbon dioxide. We'll show you the difference. I'm going to do carbon dioxide first, actually. Carbon dioxide is a lot easier. So, not surprising, it looks like this. Carbon goes in the middle. Carbon always goes in the middle. 2 oxygens on the outside. So, how many valence electrons total? How many does carbon have? We should know that all by now.
4.
4. Yes, indeedy. And oxygen has
6.
6. For a total of 12. So we should have 16 electrons. So how many electrons do we have in bonds right now? Yes, Ryan. Man, usually you speak up, Ryan. You're being just typing today. Okay, that's fair. Yeah, 4, because there's 2 bonds. So here's our 1, 2, 3, 4. So there's 4 electrons in bonds right now. So we take those out and we're left with 12. And then as usual, when we have electrons left, valence electrons left over, we start on the outside and then work our way in. So 12 electrons. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we haven't got any left over. So now let's count and see who has the right number of electrons and who has the wrong number of electrons. How many electrons does each oxygen have? Since they're both the same, we can look at either one. Does oxygen have a full octet?
Yeah.
It does, right? It has 2, 4, 6 electrons in its lone pairs, and it has 2 more in this bond. So it's a total of 8. So both oxygens are copacetic. They both have 8 electrons. So they're good. What about the carbon?
It's missing a few.
It's missing a few. Yes, it is.
Couple.
How many is it missing?
Couple. 2.
You sure?
All I know is that it's just supposed to be double bonded both sides, but we're kind of jumping a
how are
few
we going to do
steps.
that? A, how are we going to do that? And B, why are we going to do that? So how many electrons is it? How many valence electrons does carbon actually have now?
2. Like right now or in general?
No, I mean the total. When we're counting the
Oh,
total number of
4.
electrons,
It's supposed to have 4, or well,
it
8 in total.
it
I
has
think.
4. It has 2 bonds, right? So it's got these two. Whoops. It's got these two on one side and those two on the other side for 4. But that's not enough. It needs 8. Everyone's trying to get an octet, right? So
Yeah.
it doesn't have enough total electrons. Now the point you were making, which is a good point, is that the charges are messed up too. So let's look at the formal charges on the atoms. So how many valence electrons is oxygen supposed to have?
Well, it wants its shell to be filled, so 8.
Right, it wants to get 8, but oxygen as an atom by itself, how many valence electrons does it have?
6.
It's 6, right. So it's supposed to have, whoops, supposed to have 6. How many does it actually have here? Now we're
8.
looking at, well, now we're looking for formal charge. We look at the electrons that oxygen can claim just for itself, that are mine, 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 mine. So those would be lone pairs, because they're all belong to oxygen, and half of the bonds, because it can claim 1 electron from each bond. So how many valence electrons, that, like for charge purposes, does oxygen have? First, let's count the number of lone pairs. How many lone pairs does each oxygen have?
3.
3. So how many electrons is that?
3 times 2 is 6.
Yep, 6. And it's got 1 bond as well, and it can claim one of those electrons from the bond for itself. So what's the total number of valence electrons it has? So it's
Sorry,
6.
I'm having like a brain fart. Sorry.
So it's got
It's just a
6
long
in
day.
lone pairs, and it's got 1 more from the bond for a total of
7?
7. There you go.
Okay. Okay.
Yeah, so it's got 2, 4, 6, and it can claim that 1 for a total of 7. So its charge is -1. So we have a -1 charge here, and we have a -1 charge here. Now let's look at the carbon. How many valence electrons is carbon supposed to have?
4. So then
4. It's supposed to have 4. And how many
have a
does it
plus
actually
2.
have that can
2.
claim as mine, 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 mine?
2.
Just 2. Just this one and this one. So its formal charge is +2. So this is a mess. This structure is a mess. A, or 1, first problem is that oxygen has enough total electrons, but carbon doesn't. Carbon only has 4 total electrons, and it wants 8. Now, when we go to valence electrons, oxygen is too many, and carbon is too few. So we have negative charges next to positive charges, and that's in a structure, as we'll learn on Tuesday. That doesn't work. You don't have negative charges next to positive charges, because what are electrons going to want to do when these electrons are on a negatively charged atom, and there's a positively charged atom right next to it? Where do you think those electrons are going to go? Where do electrons like? I mean, they're negatively charged. Where are they going to
You
go?
like to go to the carbon?
You're damn right they do. They don't want to be, if they're going to be repelled by the negative charge of the oxygen, and they're going to be attracted to the positive charge of the carbon. So this pair of electrons is going to go there. And that forms the double bond. So we take that pair of electrons away from oxygen, and we put another bond there. And the same thing happens on the other side, because now instead of a +2 charge, so now I have a +1 charge. So I've eliminated one of the charges. And then this pair moves in, moving from a negative charge to a positive charge, like negatively charged electrons would do, and forms another bond. So this pair of electrons is now gone, and we have another bond. And that leaves us with carbon with a double bond on one side and a double bond on the other side, and no formal charges. Because now carbon has 4 valence electrons, like it should, 1 from each bond, and oxygen has 6 valence electrons, like it should. It has 2 lone pairs for a total of 4 electrons, and 2 more bonds, 1 electron each, for a total of 6. So now we have no charges, and everybody has a total of 8 electrons. So now everybody's happy. And the other thing you'll notice, that when we draw carbon dioxide like this, that's going to be our final structure. Notice that they look like what we predict from the Lewis structures. So when we draw the Lewis dot structure of carbon, we go 1, 2, 3, 4, and we predict it's going to make 4 bonds and have no lone pairs. When we draw the Lewis structure of oxygen, we go 1, 2, 3, 4, 5, 6. We predict it's going to make 1, 2 bonds and have 1, 2 lone pairs. And that's exactly what we see here, is the structure we would predict based on the Lewis dot structures. All right, so is everyone cool with carbon dioxide, how that works? Because I mean, we just learned about how to make double and triple bonds today, so it'll take a while for that to sink in. But the other thing you should look for is, what's carbon supposed to be doing? And if it isn't doing it, we've got to have a really good reason. So in this case, carbon's making 4 bonds like it should. Oxygen's making 2 bonds like it should, and having 2 lone pairs each like it should. So everything in this case looks like it should. And so that tells you that's probably the right. And there's no charges, and everybody has 8 total electrons. So it's good. So any questions on how to draw that one?
Well, I was wondering, what's the difference between like drawing the dots as bonds versus drawing lines as bonds?
Oh yeah, yeah, you can do it either way. I prefer the lines because I get confused. Yeah, because this is another way of doing it. You have 1, 2, 3, 4, 5, 6, 7. It gets a little tricky with double bonds.
Oh, I see. Yeah, because you have to have 4 of them as like.
Yeah,
4,
so you
make
can
4
do it
dots.
with just dots, but I find it really hard with double bonds, because then you have to move the dots around. But yeah, you can do it with just dots if you like. I find it much easier to do with lines and dots, because then I can immediately identify lone pairs and immediately identify electrons involved in bonds. It's not so easy when you have just the dots. So
I
some
thought they
people
meant-
do it that way, but I wouldn't recommend it.
Oh, I thought they meant 2 different things. That's why I was like confused. But
What do you mean they mean different things?
well, I thought it was like for some reason in my mind I thought like the dots were like for covalent bonds, but then I was like, wait a minute, both methods of drawing the bonds are for covalent bonds anyway.
Yeah,
So.
everything's electrons. So everything is an electron. But when you have 2 dots together, that means they're paired. They're generally not shared. They're kept by an individual atom. When you have a single dot by itself, that generally means that it is going to get paired with another single dot from another atom. So if we have, let me just clear this out. So if we have our 6, so let's put our 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. So what we would do is like, we would basically move this one down and this one over here. And so when you have these 2 paired with each other, that's a bond, that's a bond. And then this one moves over here, and then that one moves over there, and then we have there and there. So basically we get the same thing, but if you didn't have the lines, it makes it a lot harder to sort of make out what's going on. Yeah, so lines or dots, they're all electrons. It's just that if they're left as dots, they are kept by one atom. And if they're represented as lines, they're shared between the two atoms. That's the difference. And then so when we're drawing them by themselves, when we're just drawing like carbon by itself, that indicates it has 4 valence electrons, and each one of them is going to form a bond. When we draw the 6, 1, 2, 3, 4, 5, 6, when we draw 6 on oxygen, that indicates that these two are going to form bonds and these two are not.
Oh, I see. Because they're one pairs. Unless if you have something funky like fluorine.
And so we've seen that when we draw the electron configurations, when you put electrons into orbitals, once you've got 2 in there, you're done. You can't put any more in there. And so those are paired up. So we're not going to be, the next chapter we'll learn that it's not quite as simple as that, but for figuring out how they're organized in a molecule, this system works fine. When we talk about shapes, we'll learn it's a little more complicated. Okay, so let's do carbon monoxide. Carbon monoxide is cool for a lot of reasons. Well, it's toxic. That's not that cool, but anyway. So we've got carbon and oxygen, single bond. Okay, so how many valence electrons in carbon? You should know that right off. 4. Yep, that is correct, Ryan. So carbon's going to have 4, and oxygen's going to have. Somebody yell it out.
6.
6. That's right. So we're looking for 10. So how many are in bonds? How many electrons are in bonds right there? Ariana, right, 2. So Ariana, how many does that leave us to put into our structure? There you go, 8. So we have 8 left over. So I'm going to put our 8 electrons left over on each one. So we put 1, 2, 3, 4, 5, 6, 7, 8. So how many total electrons does carbon have? So in this structure, how many total, actually they both have the same number. How many total electrons does carbon and oxygen both have? Nope, not 10. 6. That's right. They each have 6. So 1, 2, 3, 4, 5, 6. So each have a total of 6. And that's, that's no bueno because they both want 8. So what are we going to do to get them there? So we're going to have to form multiple bonds, right? Because we don't have enough electrons to go around. So we're going to have to share some more.
I put a triple bond, and then
so we would take a pair from carbon. Oops. So we're going to take a pair from carbon and put it there, right? Is that what you're saying?
Yeah, and then I took another pair from oxygen
and put in there. Okay, let's see what that gives us. So that gives us, let me erase some of this stuff so we can. So what that gives us is 1, 2, 3, and then each has a single lone pair, right? Is that what we get?
Correct.
Right. So how many does each total electrons does each atom have with this configuration?
8.
8. So each one of them now has 8. So each one of them is happy with the total number of electrons they have. Now let's look and see what the formal charge is. Let's see how many valence electrons each one has. So how many valence electrons does carbon have with this particular setup? It should have 4. How many does it actually have?
5.
It has 5, doesn't it? It has 1, 2, 3, 4, 5. So what's the formal charge on carbon?
-1.
-1. What about oxygen? How many valence electrons is it supposed to have?
Oxygen has 6.
Yeah, oxygen should have 6, right? Oxygen atom by itself is supposed to have 6 valence electrons. How many valence electrons does it actually have here? It's supposed to have 6. How many does oxygen actually have in this particular structure? Is that your answer there? Is it Mient? I don't know how to pronounce your name. Is that correct? Mient? Or how should I? Okay. So 5, right? It's identical to the carbon. The structure is identical. It has 3 bonds and a lone pair. So the lone pair gives you 2, and the 3 bonds give you 1, 2, 3 more. So carbon has a charge of +1. That's weird, right? I mean, we have a structure here that where an oxygen has a positive charge and the carbon has a negative charge, but the oxygen is more electronegative than the carbon. It should be pulling electrons toward itself. And it does. It actually pulls some of the electron density on this side of the molecule and pulls it over to this side of the molecule, but it still has a positive charge. So
technically it would be polar because of the slight.
that is the odd thing about carbon monoxide. You would think it would be polar because it's charged, but because we have a negative charge in the carbon and a positive charge on the oxygen, and the oxygen is more electronegative than carbon, it actually pulls the electron cloud more toward itself, and so that's relatively balanced and it's nonpolar. So it's weird. It's a weird chemical in a lot of ways. So, it's basically a nonpolar charged molecule, huh? I mean, it should be a solid at room temperature because it's charged. It should be ionic, but it's not. It's a gas. And so that is why, that is one of the reasons why carbon monoxide is so dangerous, because it looks like oxygen. So if we look at what oxygen actually looks like, oxygen looks like this. O2 looks like that. And so you breathe in oxygen, this is what you're breathing in. And so this is completely nonpolar. Oxygen is completely nonpolar. And so when it binds to hemoglobin, to the iron in hemoglobin, it is bound and released very quickly because it's a nonpolar molecule. So it doesn't have a very, very strong attraction. It has a relatively strong attraction to iron, enough for it to bond, and so you can breathe, but not so much that it stays to the iron and doesn't come off. But this looks like it, but it has charges on it. And so it is much more strongly attracted to the iron in the center of hemoglobin. So it is a much stronger attachment. So it binds, but it doesn't come off as quickly. And so basically it binds and it's stuck there. And so basically you asphyxiate because the oxygen can't get to the hemoglobin because carbon monoxide is stuck there and it's not coming off. So that's why it's toxic. So yeah, so carbon monoxide is really cool for a lot of reasons. One of which you would predict it's ionic, and it's not. And you would predict that it is polar, and it's not. And you would say that, carbon shouldn't have 3 bonds in a lone pair, but it does. And oxygen shouldn't have a positive charge, but it does. So there's a lot of weird chemistry going on with carbon monoxide. It's a fascinating molecule. So any questions about carbon monoxide?
Are there any other molecules like it?
Oh, yeah. Yes, I mean, it looks very similar to cyanide. So cyanide basically has the same sort of structure, but instead of oxygen, you have nitrogen. And so it looks very similar. So you get the same sort of thing. And then there's a bunch of nitrogen compounds called azides, which look very similar to these. So yeah, so it's isn't chemistry fascinating? Yeah, we'll deal with a lot of these. I mean, this is one of the classic examples of a very simple molecule. I mean, it can get much more simple than carbon and oxygen, but there's a lot of very complex chemistry going on. So yeah, any other questions about carbon monoxide before we move on? Yeah, it's one of my favorite molecules just because there's so many lessons to learn from it. Okay. Oh, how about, actually cyanide ions right next, it's just 2 away. So let's do cyanide ion.
Oh, Professor?
Yeah.
After cyanide, I had a question about another one.
Oh, let's answer your question first.
Okay, for selenium tetrafluoride, does it matter where you attach the selenium? Does it have to be with the core, like in the middle, or can it be at the end?
Makes a big difference. Let's do that one.
Okay.
So selenium tetrafluoride?
Yes.
Okay. So which one do you think is going to go in the middle? You would guess selenium, right? Or would you?
Yeah, actually.
Yeah, I mean, there's only one of them. So there's 3 things going on. There's only one of them. 2, it can form more bonds than fluorine can, right? And it's less electronegative. So it's all 3 things are pointing to selenium going in the middle.
Professor?
Yes.
I got confused, and I was looking at iron for instead of fluorine. So I understand this one actually. What I was confused on is when we had, is there a possibility we're gonna have a molecule with like just say selenium and 4 irons?
No.
Okay.
No, because selenium and iron would form iron selenide. That would be an ionic compound.
Okay, so that's what I got confused on. I was looking at the wrong element, and I looked at iron instead of fluorine. So I understand this.
But you will see, like for instance, there is an ion called permanganate ion, which is MnO4 -2, I think that's the charge on permanganate. Now that is a polyatomic ion with a metal in it, but there's covalent bonds. So,
and that's what I was kind of getting at. Is there something like that, and like how do we know which one goes in the middle
less whoever has the lower electronegativity goes in the
And-
middle. Yeah.
And that would be the manganese.
Yep.
Okay.
Oh, definitely. Yeah. Any metal is going to have a lower pulling power on electrons than oxygen. Oxygen's the second most electronegative element there is. So first is fluorine. Fluorine's the king or the queen or the prince or the consort, whatever. It's the top dog in pulling electrons away, and oxygen's second, right after it. So that's why we say things get oxidized when they have their electrons removed, because usually it is oxygen doing the removing. So it's very electronegative. So you want to do selenium trifluoride while we have it up there?
Actually, can I get a do-over? Can we do phosphorus? Would it be fluoride? PF5? That's
Deca's 10.
Oh,
5 is penta.
pentafluoride.
Right. So what do we got? So we have phosphorus pentafluoride.
Yes.
Is there a charge on it?
No, it just says
Okay. So PF5. So who's more electronegative?
the
Question here.
The phosphorus.
No, nobody's more electronegative than fluorine. I put fluorine up next to anybody, and fluorine's more electronegative. So I could put like X,
Oh, yeah, okay.
F5. It doesn't matter who X is. It ain't more electronegative than fluorine. So fluorine is always going to be more electronegative than anything. So phosphorus is less electronegative.
So that's what I think I'm getting confused on is I'm trying to just look at the periodic table and I'm always going to like left and down to like indicate which one is more.
Yeah, just print out one. I'll put one up in Canvas, just the periodic table with the electronegativities in it.
Okay.
Yeah, the easiest way is to think is like if it's further to the right, it's more electronegative, and if it's further down, it's less electronegative. So phosphorus is both. Phosphorus is to the left, so it's less electronegative, and it's one more down, so it's less electronegative. So it's clearly less electronegative than fluorine.
Okay, I had it backwards. Okay, thank you.
And the other thing is that how many bonds can fluorine make?
Well, it has 7 valence electrons.
One.
Right. So how many bonds does it make? It has 7 valence electrons. How many bonds does it make?
Well, phosphorus is kind of whacked and fluorine's kind of whacked, so it violates the octet rule, and then you just have 5
It
bonds.
can't. No, it doesn't violate the octet rule. We'll talk about the octet rule.
Oh, I see. Okay.
Yeah, it can't violate the octet rule. Actually, you need to be in the 3rd period to do that. So it has 7. 1, 2, 3, 4, 5, 6, 7 valence electrons, and it's extremely electronegative. So it has 1, 2, 3 lone pairs that it keeps for itself. Nobody's getting them away from fluorine. So it can only make 1 bond. That's it. Fluorine only ever makes 1 bond because nobody is getting those lone pairs away from fluorine. That's impossible. You can't do it. So phosphorus is going to go in the middle because it can make more than 1 bond. Right. Actually, we're going to have a violation of the octet rule in this particular compound. So our phosphorus goes in the middle, and then it's surrounded by 1, 2, 3, 4, 5 fluorines, and we're going to give it the 1, 2, 3, 4, 5 bonds. Okay, so what's the total number of valence electrons for phosphorus?
7.
Phosphorus is not in the 7th group.
5.
5.
5, right? It's in the 5th group, right under nitrogen. So it has 5. So 5 for phosphorus, and fluorine, as I just mentioned, has 7. And there's 5 of them. So that's 35 and another 5. So that's 40. Man, that's a lot of electrons. 40 electrons to go around. So how many do I have in bonds right now?
10.
10, right. So I take away 10, and I have a total of 30. So 30 electrons are how many I need to put around the outside. So I'll go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's actually 30, and I'm done. So that's all the electrons. I don't have any left to put in the middle. So A, let's figure out how many total electrons does each fluorine have. Total electrons now. I will draw in the bond electrons to make it a little more obvious. So how many total electrons does each fluorine have?
8.
8, right. It's got 3 lone pairs for a total of 6. And so it's got 6 in lone pairs plus another 2 in each bond for a total of 8. So each fluorine is exactly the same. So they're all the same. They all have a full octet. Let's determine their formal charge. Now for formal charges, we just look at the valence electrons, not the total electrons. So how many valence electrons is fluorine supposed to have?
7.
It's supposed to have 7. How many does it actually have? Now we can't remember, for valence electrons, we count up the total number of bonds. I'm sorry, we count up the total number of electrons in lone pairs and then 1 from each bond. So how many does each fluorine actually have?
8.
Valence electrons, not total electrons. Total electrons, it has 8. That is true. How many valence electrons does it have?
So we're including the pairs and then the red dot, basically?
We're including the pairs because the pairs are mine. They belong to fluorine, and 1 of the electrons from, because remember, when fluorine established that bond, it was contributing 1 electron to it. Phosphorus was contributing the other one. And so they each get those back to figure out the number of valence electrons they have. So how many valence electrons does fluorine have?
7.
7. So its charge is
0. But
0.
It's neutral.
No charge on the fluorines. Now let's look at the phosphorus. How many total electrons does phosphorus have?
Is it 10?
10. That's right. Phosphorus has 10 electrons. It has 2 from each bond it can count in its total. So it has 10. It doesn't have 8. It is 10. That's strange. But what is its formal charge? How many valence electrons does phosphorus have?
5.
5. And how many does it have in this structure?
10.
Valence electrons.
5.
5. It has 1, 2, 3, 4, 5. So there's no charge in the phosphorus either. But I can hear you out there in Cyberland going, but it has 10 electrons. That is a violation of the octet rule. Yes, it is. It is a violation of the octet rule. But the reason it can violate the octet rule is because what is different? What period is phosphorus in?
The 3rd.
3rd, right. So phosphorus is in
Oh,
the
it has
3rd
an extra
period.
shell.
Bingo. So what period is nitrogen in?
The 2nd, but it doesn't
2nd.
have the extra. Well, no, it doesn't have the extra shell.
So what subshells are available in the 2nd shell?
So the first shell, you got hydrogen that has like 2, and then the second one has 8, or is that wrong?
Right. No, in the shell, that's right. The first one is 2, the second one is 8. So in the second shell, we have 8 total electrons. What are the subshells in the second shell? We have 2, so we're in the second one. So we have 2 S and 2 what?
P.
P. Do we have anything else?
That's it.
That's it, right? And so that's a total of 2 and 6. So that's a total of 8. That's all the space that any atom in the second row, the second period, that's all the room they have. So we go across carbon, nitrogen, oxygen, fluorine, all of them only have room for 8 electrons because they only have the second shell, and they only have a 2s subshell and the 2p subshell. That's it. There's no more room for any more. But phosphorus is in the third period. It has 3s2, 3p6, and what else does it have? It has 3s, 3p, and
3D10.
3d10. So because it's in the third shell, there's D subshell in the third level. There's room for extra electrons. And so you will see that this happens routinely. When you find elements like phosphorus or sulfur in particular, both phosphorus and sulfur violate the octet rule all the time. And it's because they're not in the second row. They're not in the second row. They have room for more electrons than those elements in the second period do. They're in the third period. And so phosphorus, sulfur, selenium, arsenic, all of those elements that are larger than ones in the second one, they routinely violate the octet rule. Sometimes they have as many as 14 electrons. But even if they have like a total of like 10 or 12 electrons, they still don't have a charge because they only get to claim half that number for valence electrons. So if phosphorus has 10 total electrons, only half of them are valence electrons. So 5, that's fine. Sulfur routinely has 12 total electrons, but only gets to claim half of them for valence electrons, which is 6. And that's the number of valence electrons sulfur is supposed to have. So yeah, we will see lots and lots and lots of examples of phosphorus and sulfur violating that rule all the time. So
I'm a little
be
confused
prepared when
about.
you see them. Yes.
I'm a little confused about 3D10 because I thought you don't get 3D until you pass 4S too.
No, but there is, that subshell does exist. That subshell is there. There is space there. And so if phosphorus needs a place to put extra electrons, it's there to put them in.
Oh, I see.
Yeah. So it doesn't need to go to the 4s2. That 3D subshell is there. It's a higher energy shell than 4s, yes, but it doesn't need to go any further from the nucleus to basically store a couple of extra electrons. And so, as I sort of mentioned before, a lot of times you will see violations of all these rules in the interest of having something symmetric. And notice, looking at PF5, it's completely symmetric. As you go all the way around, it's every one of the fluorines around it is the same. And then, and we'll find out when we look at the shapes that it will be a symmetrical molecule. And if nature can get symmetry, it will violate a lot of rules. Just like carbon monoxide, you have it's a symmetric molecule, even though it shouldn't be. It violates all sorts of rules, but it's symmetric, and so we'll break pretty much any rule if we can get symmetry out of it. That's true of like nuclear physics and all sorts of things, but
It also
chemistry
go-
in particular. Yes.
Does that also go for the fourth period with the F subshell?
Generally, no, because you're not going to form, remember, you only have like the total number of valence electrons is 8. So you're not going to form any more than 8 bonds. And so that's a total of 16 electrons. So you don't really need the F orbitals for that. That's a really good question, though. Yeah, generally you're not going to have more than 8 bonds. You can't. There's no more valence electrons than that. So next, who's got another suggestion for one to do? See, we got a whole bunch of different hydrocarbons there.
Can we do xenon tetrafluoride?
Sure, that's a good one. Yeah. Because you look at that and you go, what the hell is that? That shouldn't be made. Because at the very beginning of class, we learned, well, what's unique about noble gases? They have a full electron shell and they don't make compounds. Well, they hadn't run into fluorine. And so what happens with this particular instance is that xenon is big, right? Xenon has 54 electrons. So xenon is a big atom comparative to helium, which is tiny, neon, which is pretty small, and argon, which is really, really small. So those electrons are very close to the nucleus and are held on very tight by the nucleus. Xenon, on the other hand, is huge. It's a lot bigger. And so the pull on those outer electrons is not nearly as much as it is for the other noble gases. And so fluorine, being so electronegative, it can steal electrons from pretty much anybody, actually can take electrons away from xenon. So let's figure out what that would look like. So how many valence electrons does xenon have? It's a noble gas. How many does it have?
8.
8. It's got 8. So xenon's got 8. And then we know that fluorine has how many?
7.
7. It's right next to it. It's in group 7, right next door. So it has 7, and there's 4 of them. Total of 28. So we have a total of 36 electrons to deal with. So let's make our structure. So we put xenon in the middle. And let me clear this out. I want to draw this big. So we have xenon in the middle. We have our 1, 2, 3, 4 fluorine. So I'm going to put 1, 2, 3, 4 bonds. Now, what was the total number of electrons? Was it 36? Is that right?
Yeah.
28 and 8, 36, right? Yeah. So we need to put 36 electrons in there. How many are in bonds?
8.
8. So we have a total of how many to decorate our structure?
28.
28. So we start going around the outside, around the outside. Now, fluorine is always going to have 3 lone pairs under all circumstances that I can think of. I'm not an expert in fluorine. There are people who are experts in nothing but fluorine chemistry because fluorine is a pretty interesting element. But as far as I know, I think fluorine always has 3 lone pairs. So we'll do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's 6 times 4, that's 24. I have 4 electrons left. And when you have electrons left over, where do they go?
The middle.
The middle. So the xenon gets the last 4. So let's figure out how many total electrons does each fluorine have? total number of electrons?
8.
8. They each have 8, right? 2, 4, 6, 8. Total electrons, 8. So they each have 8 that satisfy the octet rule. The fluorines are all chill. So the fluorines are fine. How many total electrons does the xenon have?
$12.
Yeah, it's got 12. So it's got 4 bonds, 4, for a total of 8. So it's got 4 times 2, it's got 8. And then it's got 2 more lone pairs. 1, 2, for another 4. It has 12 electrons. So it's violating the octet rule big time. But it can because it's a big molecule and xenon is in the 5th row. So it can easily violate the octet rule. Now, what's the charge on xenon? What's the formal charge on xenon? So now instead of just total electrons, how many valence electrons does it have? So let's count up the valence electrons on xenon. Now, how many would that be? So it's got the 2 lone pairs, that's 4. And how many other, where are the other electrons that we consider valence electrons for xenon?
The ones from the bonds.
And how many from each bond does it get to keep for itself? For me, 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 me.
4.
Yeah, 1 each. 1, 2, 3, 4. 8. So it should have 8 valence electrons. It does have 8 valence electrons, and so there's no charge. There's no charge in the fluorines. There's no charge on xenon. So this is a compound that can actually form. You see xenon. So there's xenon difluoride. There's xenon tetrafluoride, and I think there's xenon hexafluoride as well. I don't know if there's octafluoride. I don't think that forms, but the other ones do. Yeah, so you can form that. So just remember, generally, who's ever going to be violating the octet rule is going to be in the middle, because it's the atom in the middle that's going to be making the most bonds. So it can violate the octet rule if, and only if, it's in the 3rd period or lower, because then there is a d orbital you can sort of stash extra electrons in if you need to. Okay? All right, what else? What else do we want to do? Did nitrogen this morning. Oh, what about acetylene? So we did ethylene this morning. This is acetylene. So instead of having 4 hydrogens, it just has 2. So who goes in the middle?
Carbon.
Carbon. Yep. So carbon, carbon, and then the 2 hydrogens are attached to each carbon. So that's basically it. So how many valence electrons on carbon? Yep, Joven, 4. Carbon's got 4. So both carbons have 4, and we know both hydrogens have 1. So 8 plus 2, 10 electrons total in the whole thing. Now, how many electrons do we have in bonds? We have 3 bonds for a total of, Jessica, right, 6. We have a total of 6. So 1, 2, 3, 4, 5, 6. So we have 4 electrons left over. We're not going to give them to hydrogen because hydrogen has 2 total. It's good. So we'll give a pair to this carbon and we'll give a pair to this carbon. So what are the total number of electrons on each carbon? Man, you're quick today, Jessica. Yeah. Was that the same answer as before? How many total electrons in each carbon? I can't tell which question you're answering. Right, fair. 6. Yeah, the 6. So it has a lone pair. Each carbon has a lone pair for 2, and it has 2 bonds, 1 on either side, for a total of 4 more, for a total of 6. So that's not enough. Carbon wants to have a full octet. So we take this lone pair of electrons, throw them in the middle, and make another bond. So I'll get rid of that lone pair. Now it gets shared. So now, how many? So now I got 2 different carbons. I've got carbon 1 and I've got carbon 2. So how many total electrons does carbon 1 have now? Yes, it will, Mien. How many total electrons does carbon 1 have? Six, right. Carbon 1 now has 6 total electrons. That didn't really help carbon 1 that much. It went from having 6 total electrons to still having 6 total electrons. So, but what about carbon 2? How many total electrons does carbon 2 have? Yeah, carbon 2's got 8 now. So carbon 2 is happy. It has the requisite number of total electrons. It has 8. It's happy. But poor carbon 1 only has 6. So carbon 2, sharing, as we know carbon loves to do, and carbon loves to share, will move that lone pair of electrons and throw it into the middle and make another bond. And so we get rid of this lone pair, goes in the middle. So now carbon 1 and carbon 2 are both identical. They have no lone pairs and 4 bonds, 3 between each other and 1 to the hydrogens. So how many total electrons does each carbon have now? Either someone type it or scream it, one or the other. I'll accept either. Yeah, Ariana, that's true.
Wi-Fi network isn't connected to the internet.
Uh-oh.
Take a look at the help section in your Alexa app.
Alexa's telling me there's a problem.
It
Okay.
looks like your Wi-Fi network isn't connected to the internet.
Can everyone hear me still?
Section in your Alexa app.
Yeah, I can hear you.
Yeah, weird. Alex is having an issue over there. Oh, well. Yeah, so we're still together. Good. I think so, because, yeah, in other words, my screen would be going glitchy or something. Yeah, so in this instance, we now have a triple bond between the 2 carbons and hydrogens on either side. So each carbon now has a total of 8 electrons. How many valence electrons does each carbon have? Since each carbon has 4 bonds and no lone pairs, how many valence electrons does each get to say it has? No, 8 total electrons, Mian. How many valence electrons? There's a difference. Right, 4. Because it only gets to claim half of the electrons in a bond. And so they each have 4 valence electrons, which they should. And so there's no charge. So nobody has a formal charge here. So in this instance, you have a triple bond. And it's one of the reasons why this gas burns at such a high temperature. It's because you have to break all of these bonds the triple bond is extremely stable. And so you need to get settling up to a very high temperature for it to burn and break those bonds. And that's why you use acetylene for like basically cutting steel, because it burns at a much higher temperature than something like butane or propane burns at a much lower temperature because they're all single bonds. This has a triple, and so that increases the temperature that you need to break all those bonds. It takes a lot more energy. Okay. We're going to deal with ozone. Actually, ozone's a pretty good one to do. Let's do ozone because ozone's a very special molecule that we're going to be, it'll be introduced in the next class. So ozone is O3. So it is not together. It doesn't look like this. That's not ozone. Ozone looks like this. Okay. So how many valence electrons for ozone? So we have 3 oxygens. So how many valence electrons is that going to be?
18.
18, right. So 3 times 6 is 18. So this whole thing should have 18 electrons. So we've got 4 in bonds. Got that bond. And we got that one. And so we have 14 left. So we start on the outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 2 in the middle. So, we have 3 oxygens. I'm just going to label them. 1, 2, and 3. So how many total electrons does oxygen 1 and 3 both have? Just since they're identical. Oxygen 1 and oxygen 3 on the outside have the same number of total electrons. How many is that? 8. Right. They both have 8. They have 3 lone pairs, 3, for a total of 6, plus they have a bond for 2 more. So for total, they have 8. So they're happy. They have a full octet. What about O2, oxygen number 2 in the middle? How many total electrons does it have? The oxygen in the middle, O2. How many total electrons does it get to have? Right. 6. It has 6. So it has a lone pair for 2, and it has 2 bonds for 2 more, and 2 more, so 6. So it does not have a full octet. So when we have that remember, when we have a central atom without enough electrons to fill an octet, we move a lone pair from the outside, around the outside, around the outside. So we move those 2 into the middle and form another bond. So now this goes away and we have a double bond on one side. Now, how many electrons does the central oxygen have now? Eight, right. It has 3 bonds, 6 electrons, and a lone pair, another 2, for 8. So every oxygen has 8 electrons. But look, they all have them in different ways. Oxygen 1 has 3 lone pairs and 1 bond. Oxygen 2 has one lone pair and 3 bonds, and oxygen 3 has 2 pairs and 2 bonds. They're all different. Each oxygen is a different situation, but they all have 8 total electrons. 3 times 2 plus 1 times 2, or 1 times 2 plus 3 times 2, or 2 times 2 plus 2 times 2. It all comes out to 8. But let's look at the formal charges. So as far as total electrons to fill their octet, everything's groovy. But let's look at the formal charge. What is going to be the formal charge on oxygen 1? So they all should have the same number of valence electrons, right? They all should have 6. So oxygen 1 should have 6, oxygen 2 should have 6, and oxygen 3 should have 6. How many valence electrons does oxygen 1 have? Seven. That's right, Ryan. It has 7. It's got 3 lone pairs, and so 2, 4, 6, and this 1 that it can claim as a valence electron. It has 7. So there's a charge on oxygen 1 of -1. And you will see that anytime you see an oxygen with 3 lone pairs and a single bond, it'll have a negative charge on it. And it has this a lot. What about O2? How many valence electrons does O2 have? Man, Ryan, you're on fire today. How many electrons does valence electrons does O2 have? Someone want to yell it or type it? Or I haven't heard from anyone in such a long time. It's getting lonely here. Someone turn their mic on. Someone talk to me. How many valence electrons does O2 have?
There's 1 lone pair and then 3 from each bond.
1 from each bond. There's 3 bonds,
Yeah.
1 from each bond.
Yeah.
So what's the total number of valence electrons?
5
Right. So what's the charge on O2?
plus 1.
Plus 1. And then what about O3?
Is there 6 valence electrons?
Right. There's 2, 4, 5, 6. So there's no charge. So again, 3 different situations, 3 different charges. Oxygen 1 has a negative charge. Oxygen 2 is a positive charge, and oxygen 3 is no charge at all. So then what's the net charge of ozone? Is there a net charge?
No.
No, there's no net charge. There's a positive charge and there's a negative charge. So there's no net charge. But when you have, that's very unstable when you have a negative charge right next to a positive charge, because we talked before, what happens to these lone pairs of electrons when they're on a negatively charged atom and there's a positively charged atom right next to it? What are they going to do? Where are they going to go? So I have a negative here, a positive here, and a neutral here. So where are these electrons going to go? From the negative oxygen 1, where are they going to go? You have negatively charged electrons on a negatively charged atom, and you have a positively charged atom right next to it. Where are those negatively charged electrons going to go?
To positive?
Yeah, they are. So what's going to happen is that one of those lone pairs is going to move to the middle and form a double bond. So now there won't be a charge on that on this oxygen anymore. Now it has 6 valence electrons, 2 lone pairs and 2 bonds, like oxygen should. But watch what happens. Where's my, oh, got my eraser. Now, what happens to the O2? How many electrons does O2 have now? Oops.
It has 10.
It is 10. And can oxygen violate the octet rule?
No.
It cannot. It cannot violate the octet rule. And so what happens is that this bond, since it's a pair of electrons, moves out to the terminal oxygen. It moves out there. So what we're left with is this bond goes away, and another pair of electrons is now on O3. So what's actually happened is now you have the exact same thing, but in reverse. So now oxygen 1 has no charge. Oxygen 2 is positive, like it was before, but now oxygen 3 is negatively charged. And so what it's going to do is it's just going to keep going back and forth and back and forth and back and forth. And what we're going to find is that this is going to form what we call a resonance form. Now, what resonance means is that basically it looks like both of these things at the same time. So on 1, in A, it has the double bond from oxygen 1 to 2 and a single bond between 2 and 3. In the other form, B, it has a double bond between 2 and 3 and a single bond between 1 and 2. So basically, it is what we call resonance. It is actually neither one of those. And what we say with ozone is that it actually has, where's my eraser? So both of these are correct. Both of these structures are correct. They're both equally likely. But since they're both equally likely, what we find is that the actual shape and size of ozone is actually right in between them. It's an average of the two. And what we say is that we have a bond and a half between each of the oxygens. We have a half bond character. So we have like 1.5 bonds on one side and 1.5 bonds on the other side. And so that makes it symmetric, because like I keep saying, nature loves symmetry. So it can't have a charge next to a charge. So what it does is basically it gives each a half a bond. And we'll talk more about this next week. But this is one of the classic examples of something with what's called a resonance structure, meaning it can be a number of different structures. Same thing with like phosphate ion and sulfate ion. There's a number of different ways you can draw them, all equally likely. Okay? So there's got to be some questions about this. This is kind of a confusing concept. But you can see how we can't really draw it in any other way, because we draw it with a negative charge on one end. That negative charge is just going to move to the other end, and then it's going to move back, and then it's going to move back. And they'll just keep moving back and forth, basically so fast. So what we see is an average of both that looks like this. So the thing to remember is you can't violate the octet rule. So oxygen can't have more than 8 electrons total. No place to put them. Sulfur can. So if it was sulfur in the middle, we could we could come up with a different structure, but it's not sulfur, it's oxygen. And this is one of the reasons why ozone is so reactive. Ozone's a very reactive gas. So it's used to basically clean things. It's used to get rid of like viruses and bacteria and everything, because it's so reactive that if you fill up something with ozone, it's basically going to kill everything in there. So also why you don't want to be breathing ozone. It's good in having the atmosphere because it helps absorb UV radiation. Not so good when it's close to the ground. So you want to have it nice and high in the atmosphere, not so close. Right. Any other ones you want to do before we call it a day?
Yeah,
Wait,
Professor. I'm just,
Yeah,
sorry.
go ahead.
Go ahead.
I was just wondering, is there a difference between the first part of the recitation, the Lewis electron dock structure and Lewis structures, or is that the same thing?
Same thing, but
Okay.
really, we're going to be doing more shapes with those. You're not asked to do the shapes right now, but those are good practice for when we actually do. I can do one with shapes if you would like, because that's sort of be an introduction to what the shapes look like.
Okay.
How about? Oh, you guys just pick one. Oh, chlorate, perfect. ClO3. There's a whole lot going on with that one. So ClO3 minus. That's chlorate ion. If you remember when we were naming our oxy ions, there was hypochlorite, chlor with 1 oxygen, and then there was chlorite with 2, then chlorate with 3, and then perchlorate with 4. So this is chlorate ion. So this is an example of one of those things that sort of go off the rails completely. Because I told you before that halogens are going to make just one bond and have 3 lone pairs. That's not the case here. It's going to look different. So chlorine actually goes into the middle of this particular structure, because I think chlorine and oxygen have almost exactly the same. Oh, I would kill for a little bit of that. Can I just have a taste? Ice cream, my poor throat. Been nattering like a fool for 2 hours here. Chlorine and oxygen almost have the same electronegativity. They're really, really close. And so we can put chlorine in the middle here, surrounded by oxygen. So 1, 2, 3. So how many valence electrons on chlorine?
That's what group it's in, right?
Yep.
So 4.
Chlorine's not a group 4, my friend.
Sorry, that's
That's
carbon.
carbon.
7. Sorry.
Oh, shh, 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 shh. Hey, Jerome, chill. They desperately want walkies. So chlorine is in which? How many
Group
valence electrons?
7.
7, right. And oxygen has
6.
6. So 18 and 7 is 25. Are we done? Is that the total number of electrons?
We have to add one more.
Right, we have to add one more because it's charged. And another thing that should tip you off when you're drawing these is that when you add all the valence electrons together and you get an odd number, something's up, something's weird. Because bonds are in pairs. That's a pair of electrons. Lone pairs are in pairs. Everything's even. So if there's an odd number of electrons, something's up. And so unless there's a radical, unless there's an unpaired electron there, and that can happen, there probably is electrons you're neglecting. Either there's more because it's an anion, or there's less because it's a cation. So you either need to add or take away to get to an even number. So we have 25 valence electrons plus one more for the charge for a total of 26. Now, how many do we have in bonds right now?
6.
6. Right, so we have a total of 20 electrons. So let's do our 20 electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 18. And so I have 2 left over. When you have left over, where do you put them?
In the middle.
In the middle. Okay. So, does everyone have the right number of electrons? Total number of electrons.
Full octet.
Oxygens and the chlorine. We need to count whether it has a full octet or not. So all the oxygens are the same right now. So how many electrons, total electrons do they have?
8 each.
They have 8 each, right. They have the 3 lone pairs for 6, and they have a bond for another 2. So they're all happy. What about the chlorine, though? Do we have a happy chlorine or a sad chlorine?
That has 8 as well.
Also has 8. Has 3 bonds and a lone pair. It also has 8. Okay, so far so good. This looks like this should work. We need to figure out what the formal charges are now. So what are the formal charges on each one of the oxygens, since they're all identical? So the formal charge we take in now, instead of total electrons, we're just looking at valence electrons.
So
oxygen, so oxygen should have 6. And how many does it actually have?
8.
8 total electrons. How many valence electrons? Remember, total electrons and valence electrons aren't the same thing.
Okay.
Valence electrons, you only get to keep half of the bonded electrons. You get to keep all the lone pairs. Those are yours. Those are mine. But you only get half of the electrons when they're shared.
So there's 7.
7. Each one of them is 7. So they each have a charge of -1. So I got a negative charge there, a negative charge there, and a negative charge there. What about chlorine? What's the formal charge of the chlorine?
It's 5 total electrons.
No, it has 8 total electrons. It has 5 total valence electrons.
Okay.
Yes, 5 valence electrons. 1, 2, 3, 4, 5. So it has, how many valence electrons is chlorine supposed to have?
7.
It's supposed to have 7, but it only has 5. So what's the charge on chlorine?
+2.
+2. So that's an issue, right? I mean, you have chlorine, one of the most electronegative elements there is, with a net lack of electrons. Well, that ain't going to work. So what's going to happen? We have chlorine with a +2 charge, and it's surrounded by negatively charged oxygens. So what's going to happen?
Wait, why is that a bad thing? Don't they want to be next to like a positive charge?
Electrons want to move toward a positive charge.
Mm-hmm.
Shut up, Alexa. Shut up. Electrons want to move toward a positive charge. So you have all these electrons on these negatively charged oxygens around the outside, and you have a positive charge in the middle. They're going to want to move to the middle, right? So this pair is going to want to move to the middle and form a double bond. So then that lone pair goes away. This charge goes away, and this chlorine is now +1. Because now it has 6 valence electrons. 6 valence electrons and only +1. So at this point, two things can happen. Either this moves again, forming a double bond. Oh, damn it. And this negative charge goes away, and this positive charge goes away. And basically what you're now left with is a single oxygen with a negative charge on it. This oxygen has no charge. There's no charge in this oxygen. There's no charge in this oxygen, and there's no charge in the chlorine. So you've eliminated a lot of excess charge and put it on just one oxygen. And now chlorine has 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5 electrons in bonds and 2 more in a lone pair for a total of 7. So it is not charged anymore. But chlorine is a total of how many electrons now? What's the total number of electrons that chlorine has?
7.
Has more than 7 total. Instead of just valence electrons, total electrons.
12.
12, right, because it has 5 bonds. And so when we're counting total electrons, it counts all those, plus another 2 for itself. So 5 times 2, 10 bonded electrons, and 1 lone pair for a total of 12. But can it do that? Is that possible?
It's
Chlorine, yeah.
Chlorine it is, because it's in the 3rd period. And so it has d orbital. It can fill the s, fill the p, and have room left over to stash some electrons in a d orbital as well. And so it can do that. So that is the structure of chlorate ion. And why it's a resonance structure is because we have 3 different oxygens. We have oxygen A, oxygen B, and oxygen C. Now that single bonded oxygen with the charge on it can be either A or B or C. Each of them is equally likely. So there's 3 different structures for this. One, the one we just drew, where the single bond and the negative charge is on oxygen A, but it could have been on B, or it could have been on C. Each one of them is exactly the same likelihood. And so just like the last structure with ozone, what you will actually find, because double bonds are slightly shorter than single bonds, because the double bond actually pulls the 2 atoms a little closer together. So we can measure this by shining light on these species, how far apart the bonds are. And so what you would predict, if this was the actual structure, that you would find 2 chlorine oxygen bonds of 1 length and another chlorine oxygen bond of a longer length, but you don't. They're all exactly the same length because it's a resonance structure. So you see the average of the 3. So instead of having a 1.5 bond average, now you have a 1 2/3 bond average. It's a little weird, but we're going to talk more about it next week.
Why doesn't the negative charge go on the chlorine? Why does it stay on the oxygen?
Oh, because generally you don't. So I guess you could. I mean, you could move this to the middle and form that, and then the chlorine would have a negative charge. Yeah, I guess that's theoretically possible, but yeah, actually that's a good point. You can look that up. I don't know if that gives chlorine 2, 4, 6, 8. Total electrons 2, 4, 6, 12, 14. I guess it's possible, But you rarely see it written that way. Yeah, why? It's a good question. I don't know. It's generally written with the one charge in the negative oxygen. That's a good point. You could draw it in that other way, with 3 double bonds. Have all the oxygens double bonded. Yeah, that's possible. I don't see it written that way, and I think it's because the bond lengths that have been observed is longer than a double bond, but shorter than a bond and a half. It's in between. So I think that's why. But that's a really good question. I will do some research on that. See, I love it when you don't think about these. Like, yeah, why can't you do that? Like, yeah, why can't you do that? I will look into that. Yeah, I think it's because they're both equally. They both have fairly equal electronegativity. So yeah, it should be sort of equally likely that the negative charge would be on either one. And if you put it in the middle, you would have complete symmetry. So yeah, I'll look into that. There may be an argument to be made for that structure. So any other questions? We'll talk a lot more about how this runs into polarity and shape on Tuesday. Then hopefully it'll start to make a little bit more sense. But basically what we're doing now is like we're building the skeleton structures, and then we're going to start thinking about them in 3 dimensions. So right now they're all like stick figures, but then we're going to start thinking about how it actually fits in 3 dimensions. Right. Yeah, go ahead.
The net charge is just the sum of all the formal charges, right?
Right.
Okay, cool.
Right. So you'd add them all together. So you noticed in each case the total charge was the same. So when all the oxygens were -1 and the chlorine was +2, the net charge was -1. And then we moved 1 pair, and then we had 2 negative oxygens and 1 positive chlorine, still -1. So it's the same. It's the same. It's different ways of looking at the same molecule. And basically, all we're trying to do is get to the lowest energy. What's the stablest version of that structure that we can get? So when we have lots and lots of charges on a molecule, that's generally not very stable. If we have positive and negative charges on adjacent atoms, that's generally not very stable either. So we try and reduce that number as much as we possibly can. Until we can't do it anymore. Great questions, everybody. Anything else before we wrap it up? So what I will do, I will change the assignment for 7 and 8 to be both due next Thursday. Give you a little extra time, okay? And if anyone else has any, I've been getting a few exam questions. I finally graded them all. There's one that I was kind of had trouble opening until I got that done. So if you have any questions about it, yeah, just drop me an email, or I'll be in office hours tomorrow at 11, okay? All right, everybody. Everybody's tired in a long afternoon. I need to steal some ice cream from my son. Cool my parched throat. So if that's all, I will see you. Have a happy day on Thursday. Man, you're getting the day off. I'm going to have to sit in a whole bunch of boring meetings. So I will see you on Tuesday if I don't see you tomorrow. Okay?
Okay, thank you, Professor.
All right, thanks. Have a
Thanks,
great
Professor.
weekend. Stay well, everybody. Don't catch on fire.